Hey everyone, just letting everybody in, take a couple minutes and we'll get started. If y'all would, I'd appreciate if you go ahead and chat me your first and last name, just so I use that as a role. There's other ways we could do it, but it's just a lot easier if you just do that for me. So just chat me your first and last name if you're in here, and make sure you do it at least before class is over. But now would be smarter because you're going to forget otherwise. But again, I want to apologize for not being able to see you guys this morning. But hopefully this will make up for it, and you'll certainly have plenty of time to ask me questions, get help, and also if you have any questions beyond this chapter, for instance, previous stuff, or if you have any test questions, or if you haven't. Yeah, even test questions will be acceptable because the last person, as far as I know, has completed the test now. Uh, but if you have any other questions like syllabus stuff, you can ask those as well. So, does anybody have any questions before we get started? And y'all can always just speak out. If you have a question, you don't have to, raise your hand or anything like that. You just speak out. But if you chat me, I should be able to see it as well. I usually open the chat window while I'm doing a Zoom meeting as well, so I can keep an eye on that. We are going into, we've already started in chapter 28. I wasn't happy with the problems we had with the abusive art law, so I'm going to just redo the that in in separate video or videos plural, and I'll put them in the this week's module instead of last week's module, just because it's the more current module. So the module I'll put up is I'll put it up right after we finish this, and then in there you'll find eventually you'll find a link to me covering the law of abuse of art, so you'd understand more critically exactly what the right results are and all that stuff, and you'll see a cleaner derivation. I know I was having some difficulties, made a couple careless mistakes, and I know that's unnerving and difficult to follow. So I don't want you guys to be bummed out and not be able to make sense of the law of abuse of art. It's pretty straightforward, other than the fact that it just takes a lot of computational power unless you can pull off some mathematical trick. So, just one more time, anybody have any questions? Oh, that was the other thing. You can chat me your questions. I think I did say that, but just in case you didn't hear it or in case I forgot to say it, you can chat me your questions as well because I'm planning on having those open. Right now, I have. It looks like 8 of you are here, and it looks like all of you have chatted me your first and last name. So I'm going to go ahead and share my iPad screen, and that's what we're going to use to cover the material. If you have access to your ebook, that might be helpful because I'm doing the book examples, but at the same time, if you can look at them, that might be a little more easy for you to do. I do repeat the diagrams to some extent, but the main thing is I need you guys to sometimes be able to see the problem in real time. Just because it's so many words, it's maybe hard for you to follow me just reading it. So, all right. So we're first starting off with, as I said, the magnetic field due to a straight wire and stuff of that sort. So, what I want to remind you is that we found. That's helpful. The dogs are barking really loud. Hopefully, y'all can't hear that. I did have a student tell me that y'all generally can't hear that. So, if it does become so loud that y'all can hear it and it's distracting, let me know and I'll put my dogs away. They're in another room, but I'll put them in a room that's closed. So, anyways, magnetic field due to a straight line. We already found basically what the magnetic field due to a current carrying wire is. And remember to obey a right-hand rule. This is a different right-hand rule than the other ones I use. This one is if you imagine this pencil is an actual wire and the current's going in the direction the pencil points, then what you're supposed to do to figure out the direction of the magnetic field around that wire is you point your thumb in the same direction of the current and make a thumbs up symbol like that, but then take the fingers and wrap them around the wire like that. At that point, you can then look at the top and you see that, excuse me, at the top, and you see that my fingers are actually curling around it in a counterclockwise direction. And that means that you should imagine now a circle concentric on the wire, and tangential to that circle are the magnetic field lines, and those magnetic field lines are tangential and pointing in the counterclockwise direction. So, in other words, if you're right here next to the magnetic field, next to the current carrying wire, right here at this point to the uh, let's say to the left of the wire, this would technically be to the right of the wire, then the magnetic field's pointing up. If it's above the wire, then the magnetic field's pointing to the left, and over here it'll point down on this side. So this side will point down, and then over here it'll point like that. So it's really hard, especially to show on a computer on a computer uh, camera anyway. So I'll draw you a picture real quick just to make sure we all follow that. So let's draw a current carrying wire. So there's one wire, one part of the wire. Here's the other part of the wire. What we're imagining is the current is going up. And now what we imagine is, and sometimes it helps just drawing a coordinate system so you can see what is in the dimensions that are perpendicular to the page and what's in the dimensions that are parallel to the page. So here's my x-axis, here's my y-axis, and this, of course, would be my z-axis. And what you can do is then imagine a circle that's concentric. In other words, its center is centered on a part of the circle and is in, or excuse me, a part of the wire, and the circle is perpendicular to the wire. So to do that, I'm going to try to imagine something like this shape, and hopefully the computer program will make this drawing a little better. Something like that. So that's supposed to be a concentric circle, and technically, to show exactly where it is in space, I need to erase this little part right here and this little part right here. And let's go ahead and erase that part. And let's go ahead and erase this part too. And now I'm going to go back and draw the little piece of wire that I erased by accident. Oops, that was supposed to be a different color. Right there and right there. And of course, the z-axis shouldn't be erased either. But now you can see that the wire is, or the concentric circle is actually perpendicular to the z-axis, which is the axis along which the wire lies, and it lies in the xy plane. Because it's perpendicular to the wire, the you might call the distance away the radius, and all that'll go into the formula I'm getting ready to give you, which you already know. But what this means is if I look to the right of the wire, notice how my x-axis is tilted it that way, and that's supposed to be coming out of the board. So if I want to draw something coming out of the board, it needs to be parallel to that. If I want to draw something going into the board or into the screen, it should be parallel to that as well. So that brings me to this direction right here is the direction of the magnetic field at a point to the right of the wire. Now, that's supposed to be exactly parallel to the x-axis, and I sort of failed a little bit on that, so let me try to get a little better. That looks a little closer anyways. So that's the magnetic field right there. If we took the magnetic field back here, that would be exactly horizontal. Again, it's supposed to be a line that's tangential to the circle. If I did over here, it would come out of the page like that. And then if I did right in front of the wire, which is what this means, then it would be this way. So that's the magnetic field direction at every point. And that should remind you of the vector I've been teaching you about, theta hat. That's sort of the beauty of introducing the spherical coordinates is theta hat points in the direction of the magnetic field, or negative theta hat if the current was going the opposite way. Now, the formula that all of this I drew for was specifically that B, the magnetic field, a distance r away from the wire, the center of the wire, is given by mu 0 I over 2 pi. And since I used a capital R down there, I'll use a capital R here. And then I'd say specifically theta hat, because that's really the direction of the theta hat is exactly what's described by these little green arrows. Remember what theta hat really means in general is if you imagine some point in space, let's say right here, and this is one, this is actually from polar coordinates. It's also from what we call cylindrical coordinates. And if you imagine a point in space, we could actually define that point as x comma y comma z, but we could also define it as r comma theta comma z. In this case, z would be 0, but the main point is this is theta. And then if you go off in the radial direction, and make it a single unit vector, meaning its length is just 1 unit long, then that vector would be the r hat vector. And notice it points in the direction of increasing r. And R, of course, is the variable that I said the point would be. And then perpendicular to that, in other words, at a 90-degree angle, is the theta hat direction. And that's what's showing there. And then, of course, perpendicular to both of those would be the k hat, and that's the coordinates that we use for the coordinates in the cylindrical coordinates. So, for instance, that point P was, as I said, x comma y comma z, but it could also be written as r, theta, and z. Some books will choose to call that rho, theta, and z because the rho is not technically the same as the r from spherical coordinates because the r from spherical coordinates actually has the z component as well. So, anyways, that's really what the magnetic field due to a current carrying wire is a distance r away if the current is I. Any questions on that part? I know I've covered this like 3 or 4 times now, but I just want to make sure everybody's on the same page with that. Now we'll look at example 28.1, and I'll say right here, example 28.1, calculation of B narrow wire. An electric wire carries a DC current of 25 amps vertically upward. What is the magnetic field due to this current at a point P 10 centimeters due north of the wire? So again, I'm going to draw a wire real quick just to get an idea of what we're talking about here. So this is a wire. And then I'm going to lay down my X, Y, Z axes again. So that would be one. This could be one as well. And that could be one. That could be one. That's all basically just the XY plane and the XY coordinates. And then perpendicular to that going upward would be my Z coordinate. Now, in order for me to make it like we're used to in class, then I would say this would be the x-axis, which also refers to due east. This would be the y-axis, which also refers to due north. And this would be south, and this would be west, like that. So they're asking specifically in what direction would the magnetic field, or actually, what is the magnetic field due to a current at point P 10 centimeters due north of the wire? So what we're imagining is going down here 10.0 centimeters, and it's due north of the wire. According to our right-hand rule, or to the diagram above, we see that this current carrying wire should create a magnetic field pointing into the page here, which is in fact the westward direction, as you can see. So that's the actual direction of it, which means it points to the west. They did give us numbers. The numbers they gave us, of course, were I is equal to 25 amps. They gave us the distance away, which I used a big R up there. I'm just going to use a little r for this one. And that's supposed to be the distance measured perpendicularly from the center of the wire to the point at which we wish to know the magnetic field. And this one's supposed to be 10 centimeters, which I'll write like that. And what they're asking for is B equals question mark. So B is equal to mu 0 I over 2 pi R. We've already worked out the direction. The mu 0 is 4 pi times 10 to the negative 7th Tesla meters, Tesla meters per amp, like that. Then that's multiplied by 25 amps, and then that's divided by 2 pi, and then 0.10 meters, like that. So when I do this calculation, I get, notice the 4 pi with the 2 pi downstairs just becomes 2 times 10 to the negative 7th. So in other words, I'm going to say this cancels out with this, leaving just a 2. So I say 2 times 10 to the negative 7th times 25. And now I'm going to divide that by just the plain 0.10. And that gives me 5.0 times 10 to the negative 5th. Tesla. That's the magnetic field, and as I said, it points west. Any questions on that one? Okay, this stuff will be posted to my Not only will this video be posted to my YouTube channel, but the notes will be posted in my Google Docs for 242, so you can see them there as well in case you don't get them later, or if you end up having to miss class or whatever and you didn't get to take notes, they'll be there. Now let's look at example 28.2. Example 28.2 says magnetic field midway between two currents. Two parallel straight wires are 10 centimeters apart, carry DC currents in opposite directions. Current I1 equals 5.0 amps is out of the page, and I2 equals 7.0 amps is into the page. Determine the direction, the magnitude and direction of the magnetic field halfway between the two wires. So what we have is I1 equals 5.0 amps, and that's supposed to be out of the page. And I2 is equal to 7.0 amps, and that's supposed to be in the page, into the page. And they're supposed to be 10 centimeters apart, so I'm going to say D is equal to 10.0 centimeters like that. And they want to know B equals question mark at midpoint. So if I want to draw the current carrying wire pointing out of the page, then what I'll do is just draw a circle, and this will be representing as if we're looking as the current is shooting right in my eyeball. So the wire is actually perpendicular to the page. And then I'm going to go over a distance of 10 centimeters, which I'll pretend is like this distance right here, like that. And then we have the 7 amps is coming out of the or going into the page, and that's supposed to be that way. So this is the I2 equals 7.0 amps, and this is the I1 equals 5.0 amps. And we see that, and specifically, we would like to know the magnetic field at this distance, which should be roughly right about here. 5.00 centimeters over is the midpoint, and we want to know what the magnetic field is right there. So I'll put a little P there just to represent that as the point. Now, in order to understand this, we need to have some idea what direction the current is creating a magnetic field in. So in this case, we'd say the magnetic field here, which looks about 3, 4 units. So 1, 2, 3, 4, something like that. So the magnetic field for the current coming out is actually going in a counterclockwise direction like this, and obviously the end of that didn't turn out so good. So something like that, and that means the magnetic field, I'll call this B1 because it's due to current I1. And then we have another circle representing the magnitude of the magnetic field of the wire I2. And in this case, I'm going to draw it like this, and this way is in fact in a clockwise direction. So this points that way, that points this way. But since it's in a clockwise direction in this case, that also means that the magnetic field due to this side is B2, and that's due to the current I2. And I made it a little longer because the current's bigger. So the main thing that we see is because it's midway between them, they're both actually going to be either parallel or anti-parallel, since in this case the two wires were the currents were in opposite directions. They're creating magnetic fields that point in the same direction, dead center between them. So I just need to calculate the magnitude and then add them because they're the same direction. So the way I do it is this. B1 is equal to 4 pi times 10 to the negative 7th Tesla meters per amp times 5.0 amps divided by 2 pi times 0.0500 meters. And that should give me, notice again, the 2 pi and the 4 pi cancels out to give me 2 times 10 to the negative 7th times 5 divided by 0.05. That gives me 2 times 10 to the negative 5th Tesla. Now I do B2, which is again 4 pi times 10 to the negative seventh. I'm going to leave the units off this time. 7.0 amps divided by 2 pi times 0.0500. And this time we get 2 times 10 to the negative seventh times 7 divided by zero point zero 0.05, and that gives me 2.8 times 10 to the negative fifth Tesla. So B total at P is equal to 4.8 times 10 to the negative fifth Tesla upward. Because remember, a magnetic field is a vector quantity, so you're not supposed to just give the magnitude unless they explicitly say you only have to give the magnitude. Otherwise, you got to assume they want the magnitude and direction. And this one actually asked for both, so it was a little clearer. Anybody have any questions on that? Okay. Example 20 or 28-3 is a conceptual example, but it's a really good one, so I'm definitely going to take time to write this one out for you folks. So here's the example. I hate this stupid program. It always aggravates me. Example 28.3. Again, it's a conceptual example, and they're asking magnetic field due to four wires. Figure 28.4 shows four parallel wires which carry equal DC currents into or out of the page as shown. In which configuration, A or B, is the magnetic field greater at the center of the square? So that's what we're trying to figure out. And we have two different configurations. So I'll draw them right here. I'm going to say here's a circle, here's a circle, here's a circle, and here's a circle. All of those represent wires. And if they got an X in it, that means the current's going into the board, like this one and this one. And if they got a dot in it, that means the current's coming out of the screen or board, like this, like these two. And then the other configuration I'm going to draw is this, this, and this. And in this case, we've got these diagonal ones going into the page and these other diagonal ones going out of the page. So what I want to do is try to figure out dead center what is exactly the magnetic field. So I'm going to put a dot right in the middle, and what I'll do is I'll put a little black one right, a black mark right here, and that's just for me to indicate that the magnetic field due to that one will be represented by black. The magnetic field due to this one will be represented by blue. The magnetic field due to this one will be represented by red, and the magnetic field due to this one will be represented by green. So applying our right hand rule, and remember, you guys need to be able to do this. So I want you to think, predict in real time exactly what direction this will be before I write it down so you can get some practice. And then, of course, if you get it wrong, make sure you figure out why it's wrong. And if you don't, you can't figure it out, then ask me. So we're looking right here. We've got the top left wire, that's the black one, and that one is a current going into the page. So I imagine my right hand like this with my thumb going into the page and I curl my fingers around. That seems to make a clockwise direction. So the black magnetic field, the wire or the magnetic field due to the wire with a little bit of black on it is going to point that way. And notice they're all identical currents and they're all identically distant from the center. So all of these arrows should technically have the same length because the length represents the magnitude and all the individual magnitudes should be the same. Now I'm going to do the top right one, which is the blue one, and that's going into the page as well. So again, we get in that case that it's supposed to be uh, in this case, it'd be again clockwise. So down here at the center, that means the blue magnetic field would point this way. Again, all these arrows are supposed to be the same direction. Now, if I do the red one, this is a counterclockwise direction for the red one. So the red one should give us this little vector right here and it should be in the exact same spot and the exact same length as the black one. I just needed to make sure y'all can see it. Now, in the case of the green one, it's going to be counterclockwise as well, and as a result of that one, it's going to be a magnetic field pointing this way. So that's the four magnetic fields you get from those four wires, and you see that basically the Y components, the vertical components, are going to cancel each other out, and you're only going to get a total of a horizontal vector pointing to the left. Now let's do the other two, and again I'll say this one's black, this one's blue, this one's red, and this one's green. So starting with the black one, again, we're also starting at this dot as the center. So starting with the black one, that is a current carrying wire carrying current into the page. That means it's going to be in the clockwise direction, and the clockwise direction would point it right here. Now the blue one is coming out of the page. That makes it counterclockwise, and that would cause it to actually point in this direction right here. And then we do the red one. The red one is going into the page. That means it's going to be clockwise, and then clockwise at this particular location would indicate that vector. And then finally, green is a current coming out, and that makes it a counterclockwise magnetic field. And that magnetic field should point, in fact, this way. So you should be able to see that the sum of all the B's is equal to zero in this case because they all had the same magnitude. The red one cancels out the black one completely. The green one cancels out the blue one completely. So that's zero. This one's going to result in the summation of the magnetic fields is equal to something like this. So clearly, the one that produces the largest magnetic field would be this configuration on the left because the question was in which configuration A or B is the magnetic field greater at the center of the square. Anybody have any questions on that? So make sure you guys can do that. Y'all should be able to do these kind of drawings at the drop of a hat. Should be no issue whatsoever for you to be able to do it. Again, anybody have any questions? All right, let's move on then. Now we're going to get into something a little bit more exciting. This is the forces between two parallel wires. So let me work out the details of what's going on here. Uh, Forces between two parallel wires. Now, this could mean, for instance, you could be talking about one wire imposing a force on the other, and you might be asking, what is the force on wire one as a result of wire two? Or you could ask for what is the force on wire two as a result of wire one, that sort of thing. Let's start off with the two parallel wires, just like your book is doing. So I'm going to say, here's one parallel wire, one of the two parallel wires. And we're going to say the currents in this case are parallel. So this is I1. And then over here is I2. So there's the current there. And in order for us to figure out what the force is, we're obviously going to need to know the distance between them. And I'm going to assume that that distance is D. Okay. So in order for us to figure out, for instance, F12, which is defined to be the force on wire, or actually, I should really say it's a force on the wire, but it's only a force on the wire because the wire is carrying the current. So it's more like a force on the current. So force on current one due to the magnetic field caused by current two. Okay. So normally F12 means any force on object one as a result of object two. In this case, I was gearing it towards magnetic field. So I had to put a little bit more wording in it. But remember, when I write that definition, it's just in this particular case what this definition is. In general, F12 just means the force on one as a result of two. So that works fine. But in order to do that, what we need is an equation that gives us the force applied to a current due to a magnetic field, and that's the F equals Bill equation. So remember we had F equals Bill, and F equals Bill works, but it's sort of out of order. It's not that helpful. It's helpful to remember it because it has B, I, and L, and you know those are the factors that they turn on, or they depend on. But the order is wrong for you to determine direction. So I like to write it like this: the force dF is equal to I dL cross B. Okay. Now DL is just a infinitesimal vector lying along the wire pointing in the direction of the magnet or of the current. So the DL has to point in the direction of the current I that's actually causing the force on the wire. Okay, so with that in mind, we can say since in this case the DL doesn't change from one part of the wire to the next, nor does its relative orientation with respect to the magnetic field change from one spot to the next. So if I were to choose to integrate this, then what I would get is F is equal to I L cross B. This is what I mean why I should say F equals Bill is not that helpful because it's in the wrong order. And if you need the order to figure out what the right hand rule is, then that's not going to help you. F equals Bill is going to screw you up. So it should be F equals Ilba, which sort of sounds like the island that Napoleon was sent to, so you can maybe remember it that way. So what I'm going to do here is I first got to figure out what is the magnetic field caused by 2 at 1. So what is B at 1 caused by 2? Again, I'm just saying 1 and 2, those are supposed to represent current 1 and current 2. So current 2 is creating a magnetic field. We know using our right hand rule that if I looked from above, it would make a counterclockwise circle on centered on that wire. So if I look to the left of that wire, the magnetic field should point out of the board. So I'm going to say it will point out of the screen and have a magnitude of B at 1 due to 2 is equal to mu 0 I2 over 2 pi d. Okay, so now I've put all the necessary numbers and subscripts on there so you can see exactly which current is causing the magnetic field and what is the magnetic field. So I've answered the first part. Now I need to know what, oops, I'm going to start spelling what without an H. What is the force on one due to that B field? Well, that is F12 is equal to IL1 cross B at 1 due to 2. So that's really what it's supposed to be. I can go ahead and draw the magnetic field right here. I'm not going to try to show it in 3D. I'm just going to draw it like this so we recognize that the magnetic field is coming out. So this is B at 1 due to 2. And notice it's pointing out of the page. Now I can say DL could be that vector. And therefore IDL cross B, you take the IDL, which goes up, and you cross it with B, which points towards us, then that tells us that the force is to the right. So we can now say F12 points to the right from the right-hand rule. Remember that right-hand rule that we're using here for cross products is the index finger points the direction of the first vector, the middle finger points the direction of the second vector, and the thumb points in the direction of the answer, which is a cross product. So when you're doing a cross product, the index finger points in the direction of the first vector in the cross product. The middle finger points in the direction of the second vector in the cross product. And then your thumb points in the direction of the force that results from it. And remember that middle finger, I normally say you hold them 90 degrees to each other, but in principle, the vector could actually be almost parallel. Just the point is when it gets to parallel, so that the angle between these two is zero. When that happens, the cross product zero. Or if the finger is anti-parallel to the index finger, that means the angle between them is 180, and that also gives a zero for the cross product. So it should be somewhere between 0 and 180. But the main thing is it is possible to be exactly perpendicular, and then you just get IL times B. All right. So now we have the formula that we need. And in fact, since we see they're all perpendicular, we don't have to have the trig function that's normally associated with the cross product or the actual magnitude. Remember, the magnitude of a cross product, A cross B, is A times B times the sine of the angle between them. This one doesn't need that sign because the sine is taken of 90 degrees, which is just 1. So in this case, what we get is the force is going to actually be F12 is going to be equal to, and this, by the way, had to be I1. I forgot to write the subscript 1 on the current. So it's going to be I1 times L1 times, now I've got to write the current or the magnetic field that we just calculated, which is mu 0 I2 over 2 pi d, like that. So, and I shouldn't have a vector on there because that's not a vector equation. So let me take that off. But that's the equation. Now let me write it in a more succinct form, if you will. So the force on 1 at 2 is actually equal to, and I'm trying to write it the same way they did. Let me double check what order they're putting all their symbols in. Yeah, so they're doing mu 0 over 2 pi as a multiplier out in front. So that's just, a convenience thing by putting those constants out in front. And then all we have is I1 times I2 over D. And then all of that times, in this case, it would be the wire I1, or the length of the wire L1. And yeah, I did use a capital there. Okay, I was just making sure your book uses that script L, but that's fine as well. Uh, so I just calculated, which notice this formula is going to be different from the book says, because the book was calculating the force on 2 due to 1. I'm calculating the force on 1 due to 2. So that's our answer. And what we say is they attract if I1 and I2 are parallel. Okay, so there's literally a force of attraction between two current carrying wires that are having the current go in the same direction. And from this, you should be able to figure out that if one current's going up and the other current's going down, they're anti-parallel, and therefore they would be repulsive. So I'll write this. Therefore, if anti-parallel, then the force is repulsive. Okay, so parallel currents attract, anti-parallel currents repulse. And that's the formula. Now you can see from the symmetry of it, if I wanted to write the force on 2 due to 1, then the mu 0 and the 2 pi, that's not going to change. And it doesn't matter if I write I1 and then I2, But to keep it in the same order as the suffixes, I'll write I2, I1, and then divided by D. All of that's exactly the same as the other formula. The only difference is now we're going to have L2 as the uh, length that we're considering. So this is the force on I2 due to I1. And again, it has the same rules: attractive if they're parallel, and repulsive if they're anti-parallel. Any questions on that? All right, looks like no one has any questions. I am looking at the chat window, by the way, so if y'all do type me a question in chat, I will see it, but you're also just allowed to just speak up and say it. You don't have to only type it. All right, we'll move on then. So here is example 28.4. And example 28.4 says force between two current carrying wires. Two wires of 2.0 meter long appliance cord are 3 millimeters apart and carry a current of 8 amps DC. Calculate the force on one wire. Calculate the force one wire exerts on the other. So they're not really caring which one's wire one, which one's wire two. They just want to know the force. So two wires, 2 meters long. So what we have is L1 equals L2 equals 2.0 meters. Are 3 meters apart, 3 millimeters apart. So D equals 3.0 millimeters. And the currents I1 equals I2 equals 8.0 amps. And they said two wires of a 2.0 meter long appliance cord are 3.0 millimeters apart and carry a current of 8.0 amps DC. Okay, calculate the force one wire exerts on the other. So they're not even telling you if this case, if these wires are parallel or anti-parallel. Generally speaking, if you're talking about a appliance wire, for starters, they are normally AC, not DC. But the wires, basically, you can see normally the wire will be flat and it'll have like a groove. It looks like right down the middle of it. They don't always have that, but some of them do. And that groove is more or less showing you that, hey, if you go to one side of the groove, there's going to be a wire, and if you go to the other side of the wire, the groove, there's going to be another wire. And normally that means one wire is taking the current to the appliance, and the other wire is returning it back to either ground or back to the battery or power source or whatever. In other words, one would be the black wire that I talked about regarding light receptacles, and the other one would be the white wire that it returns the current back in. So, anyways, with that in mind, we're not told any of that. The only thing is we're really asked for the magnitude. If the two are anti-parallel, we know that they would repel, and we'd expect the wires to try to separate like that. But let's go ahead and calculate F12 is equal to mu 0 over 2 pi I1 I2 over D times, in this case, we're going to say L1 like that. And it doesn't matter because it's the same numbers either way. So we're going to get 4 pi times 10 to the negative 7th Tesla meters per amp divided by 2 pi. And again, we know this number is 2 times 10 to the negative 7th. And the reason why I point that out is in the next section of this chapter, they talk about how we use two current carrying wires to define the ampere, and then we use the ampere's definition to define the coulomb. And oddly enough, what they say is 1 amp is defined to be the current that allows two wires running parallel to each other to attract each other with a force of 2 times 10 to the negative 7th newtons per meter of wire. So you're taking two very, very long wires, you're having them a very specific distance apart, and they're specifically 1.00 meters apart. And when you do that, those two wires 1 meter apart and very long, that means they must be at least, 10 to 20 meters bare minimum length. And if you find that the force per unit length is 2 times 10 to the negative 7th, then that means those two wires are each carrying 1 ampere. Okay, that's the modern definition of an ampere. And then the coulomb is defined to be the number of charges that pass a certain point or come out of a wire every second if the wire is carrying 1 amp. All right, so now let me show you the rest of this. This is I1, which is 8.0. Forgot I changed color there. 8.0 amps times 8.0 amps divided by D, which in this case we said is 3.0 times 10 to the negative third meters, and then times the length, which we said was 2.0 meters. So that's the actual rule, and that's the formula. So we're going to say 2 times 10 to the negative seventh times 8, and then I'm going to divide that by, or actually, let's go ahead and say times 8 times 8. So I said 2 times 10 to the negative 7th times 8 times 8 times 2. And then I'm going to divide that by 3 times 10 to the negative 3. And that gives me 8.53 times 10 to the negative third newtons is the length, is the force. Okay. And that's the same number that your textbook gets. And again, if the two wires, which is normally what they are when they're talking about a wire for an appliance, one wire is taking current to the actual device or appliance or whatever, and the other wire is returning the current back to the power source. So they would be anti-parallel and they would be therefore repulsive, but they didn't actually ask for that part here. Any questions on that one? A couple people have come in since I've started, and again, it's not a big deal. But do chat me your first and last name. I'm using that for roll. There's other ways I can get it. I know it's just a lot easier if y'all just chat it to me, so then I'll have it in the chat. So please chat me your first and last name. That way I can know you're here today. We just finished example 28.4, and we're going to move on to example 28.5. Example 28.5 says suspending a wire with a current. A horizontal wire carries carries I1 equals 80 amps DC. A second parallel wire, 20 centimeters below it, must carry how much current? I2 so that it doesn't fall due to gravity. The lower wire has a mass of 0.12 grams per liter, or excuse me, per meter of length. I saw the L for length and just read liter instead of meter. I don't know. Anyways, we're going to write down that data. The data is I1 is equal to 80 amps, and that is DC. And he keeps mentioning that, by the way. If it's AC, basically what happens is the wire switches direction so rapidly that you really don't get much ability to detect the magnetic field at all. But it could cause problems, for instance, with electronic devices nearby and stuff like that. So just that's part of the reason why he's telling you it's DC so that you'll know, oh, this is a current. You could actually measure it, that sort of thing. Second wire 20 centimeters below, so that means D is equal to 20 centimeters. I'm going to call that 20.0 underscore centimeters. And they want to know I2 is equal to question mark. And what we know is M2, or let's say lambda 2, which remember this is the lambda that we used in physics 241, the mass per unit length, is equal to 0.12 grams per meter. So that's the lambda that we're looking at. Now, here's our picture. We want these to be attractive, so they need to be actual parallel wires. So I'll draw this one wire right here. And this is I1. So I1 is going that direction. And what we're going to do is say, okay, down here is current I2. And I should stop it there. And that is I2 equals question mark. This is 80 amps. And this distance between them is 20.0 centimeters from here to here. And what we know is there's a force of gravity pointing downward. And if you consider just a 1 meter segment, which is what we're sort of focusing on right now, I'm going to imagine that I'm zooming in on just this section right here. And let's say this distance from here to here is 1.0 meters. And that's the same thing with this section and this section. And therefore, if it's 1.0 meter, we know that the force would be, uh, I'm going to refer to this one. This force is now going to be uh, 0.12 times 10 to the negative third kilograms per 1.00 meter times 1.00 meter times G, which is 9.80 meters per second, and that quantity gives me 0.12 times 10 to the negative 3 times 9.8, because it's one, it's multiplied by one and divided by one. That doesn't do anything. So this force is going to be 1.176 times 10 to the negative third newtons, and we need that force to be actually equal to the force of attraction between the two wires. So we know that it's going to have this other force acting up on it. That's F. Let's call it just FB. And really, we could also call it the force on 2 due to 1. That would be acceptable as well. So now we're going to work that out. FB equals F21 is going to be mu 0 over 2 pi times I2 times I1 over D, which is written right there. And then, of course, we're seeing the force on 1, so that's going to be times L1, but we've already decided that that's going to be 1 meter. So we can go ahead and write this as follows. We're going to say 4 pi times 10 to the negative 7th Tesla meters per amp. I wrote a meter down there because I said the word meter at the same time I wrote the A, and that just didn't pan out, over 2 pi times I2, which we don't know, so I'm just going to write I2 here, times I1, which is 80 amps, divided by 0.20 meters, and then times 1.00 meters, like that, and that's got to equal 1.176 times 10 to the negative third newtons. So what we can do is go ahead and compute all this stuff. So I'm going to say 2 times 10 to the negative 7th times 80 divided by zero point 0.2 is equal to 8.00 times 10 to the negative fifth. And the units here, the meters cancels out, the amp cancels out. We got another meter up top there. That works out okay. So Tesla meters is the answer, the units here. So I'm going to say this is Tesla times meters, and that quantity is multiplied by I2, and that's equal to 1.176 times 10 to the negative third newtons, so that we should ultimately get I2 is equal to 1.176 times 10 to the negative third newtons over 8.00 times 10 to the negative fifth Tesla meters. Hold on, everybody. My dogs are raising heck close. My nephew's trying to get in the house. I'll be right back. It'll take about 2 minutes. Not even 2 minutes, 1 minute. Never mind. They got in. Sorry about that, everybody. So now I'm going to take this number and basically do the division. So 1.176 times 10 to the negative third divided by 8 times 10 to the negative fifth gives me 14.7. Oops, I'm on. Okay. Equals 14.7 amps. I only had really two sig figs everywhere, so this should have worked out to be only two sig figs, but that's the amperage that we need basically 15 amps to 2 sig figs or 14.7 to 3 sig figs. Anybody have any questions with that? I didn't show you the way the Newton can cancel out with a Tesla meter to give the actual ampere, but that's a good practice or a good exercise for you try guys to convince yourself of. So, anyways, anybody have any questions on that? All right, so I'm not seeing anybody typing any. I don't hear anybody asking any. So we'll press on again. As I said, the next section, 28.3, was definitions of the ampere, and they basically just define, like I said, it's the same diagram that we use for example 28.5, but basically you take two really long wires and if they both have exactly 1 amp going through that, then you can use that as the standard amp, provided that the force on each meter of wire is 2 times 10 to the negative seventh newtons per meter. And of course, that has to be at a distance of 1 meter. So that's what the definition of 1 ampere is. And then, like I said, 1 coulomb is 1 ampere times a second. So if you collect the amount of charge coming out of a 1 amp current for 1 second, then you'll get exactly the correct amount of coulombs. Those are called operational definitions because you can actually create a device and then operate it to see the actual value. So here's the big part of the remainder part of chapter 28, which is Ampere's law. And your book talks about how to derive it and that sort of thing, but I'm going to go ahead and state it and just use it. And it's very much consistent with the way we did Gauss's law. So here's what it is. The closed integral of b dot dl. Notice it's b dot dl instead of dot da because the integral in Coulomb's law, or excuse me, the integral in Gauss's law was a surface integral. So it was dot da and it was over a surface. That's a different type of integral than over a path, which is what this one is. This is a path integral or a line integral. And specifically, it's supposed to be over a closed loop, just like before when we did Gauss's law, that was supposed to be over a closed surface. Again, just like Gauss's law, the law is always valid, but you can't use it this weird way we're using it to extract the integrand out of the equation unless you have certain symmetries. In this case, the symmetry has to be an infinitely long cylindrical wire, or it has to be a solenoid, or it has to be a toroid. And we'll show you what those are. You probably already know a solenoid, but a toroid you might not know. So we'll talk about that. But Ampere's law is the closed integral of b dot dl is equal to mu zero I enclosed. So what we mean by that is if you had a current carrying wire, let's say like this, and it has a current I like that. Now we're going to imagine a closed loop around it. And for symmetry, we're looking for, just like we did with Ampere or with Coulomb's law, we looked for the symmetry of the electric field so that we could create a surface on which the electric field was a constant because when we did that, the closed integral of E dot dA, since the electric field is just a constant, became E times the integral of dA, and therefore it just became the electric field's magnitude times the surface area of the surface on which the electric field was a constant. Well, this is the same sort of thing. We're trying to choose a path that we can integrate along such that the magnetic field is going to be a constant on it and is always going to have sort of the same relative orientation with the magnetic field and the differential line element segment of that path. So in this case, we can tell that we would like to have a path on which the magnetic field is a constant. And what we've learned is that the magnetic field is a constant on any circle that's concentric with the center of the wire and perpendicular to the wire. So in this case, what I'm going to imagine is a path that is perpendicular to the actual wire like this, and it's centered on the wire. So the distance from here to here is, for instance, the distance r, and from that we now know that the magnetic field everywhere will be a constant. That's the big trick. Now we'll later learn that there's a missing term on the right hand side of the closed integral a dot d b dot dl equals mu zero I enclosed. There's another term there that Maxwell recognized was missing and derives it. And we learn that later in a later chapter. But right now it doesn't matter. Specifically, right now your idea is that only a current can create a magnetic field other than the magnetic phenomena that we learned in magnesia about certain rocks that attracted one another and repelled one another. Other than that, we only thought currents do it. But once Maxwell fixes Ampere's law by putting that term on the end, we'll see that a changing electric field can also create a magnetic field. So that's kind of a neat thing that's going to come. But this is Ampere's law, and we work it a lot like we did Gauss's law. So, for instance, what is the magnetic field? I don't know why I wrote that capital. What is the magnetic field at a distance r from an infinitely long wire carrying a current upward? So that's the question. And when I say distance r from it, we mean a perpendicularly measured distance. So I want to put that in there. Perpendicularly, oops, measured. So we'll say one, by symmetry, we hypothesize B is equal to some B that likely only depends on R, because if it depended on some other variable, that would be completely inconsistent with what we've seen for an infinitely long wire. So it's B of R, and it's going to point in that theta hat direction like I described for you before, which I'll just say use right hand rule. And I mean by that, use the right hand rule to actually determine the uh, direction of the magnetic field. Okay, so we've now made our hypothesis. Now I'm going to say to compute left-hand side, left-hand side, closed integral b dot dl is equal to the integral of b of r theta hat dotted with, now dl is going to be, for instance, we could say this and this. We could say this is our x-axis, this is our y-axis, this is our z-axis, then this would be the angle theta, and this would be the angle d theta, so that this little differential right here is dl is equal to r d theta theta hat. So we're going to say that one's going to be r d theta theta hat. And like we learned before, the dot product is a linear operator, so we can pull all the scalars out in front and just let the dot product act on the individual vectors. And because of the way we chose this line, this Amperian loop, Because the way we've applied this Amperian loop, we know that B of R is going to be a constant on it, so I can write the B of R out in front times the integral of R d theta, theta hat dot theta hat, and the R is actually going to come out in front too. I should have put that out there before. I'll do that now. I'm going to say B of R. Now I'll put this one in red so you can see that that's the change times the integral d theta from theta equals 0 to 2 pi because we got to go in a complete loop and therefore the radians is up to 2 pi. And of course, theta hat dot theta hat is just 1. So we get 2 pi r b of r is the left-hand side. Okay. Now, whenever you're doing a Gauss's or an Ampere's law problem, the left-hand side is always going to turn out to be some current times the length. It might be, or excuse me, some magnetic field times the length. It might be magnetic field times the length plus magnetic field times another length or something like that, but it's still always going to be in the form of magnetic field times the length for the left-hand side. If it's anything nastier than that, then you've done something horribly wrong and you shouldn't be doing it. Okay. So that's the trick with this. And there's only three different varieties, just like there was with Gauss's law. There was only, spherical symmetry, infinitely long cylindrical symmetry, and flat infinitely planar symmetry. In this case, it's only infinitely long cylinders, solenoids, and toroids. So now I've done the left-hand side. Now I want to compute the right-hand side. 3, compute the RHS. And the way we compute the right-hand side is right-hand side, that's equal to mu 0 I enclosed. Now here's the trick though. I was imagining this Amperian loop and I chose to traverse this Amperian loop in a counterclockwise direction as seen from above because that happens to be parallel to the magnetic field. If the path along which you integrate is consistent with this right hand rule that I'm getting ready to give you, then the current should be I. If it's inconsistent with that right hand rule, then the current should be negative I. Now, here's what the right hand rule is in this particular case. Again, you're just doing your fingers curling around, your thumb sticking up. What we're saying is if you curl your fingers around the path of the integral, in the same direction that the integral is integrated along, then your right thumb points in the direction of a positive current. So in this case, I was doing counterclockwise and my thumb pointed up. Well, that happened to be the same direction as the current. So the current in this case is just going to be I and it's positive because it's consistent with the right hand rule. So it's going to be positive. Oops. It's going to be positive mu 0 times I. Now for set left hand side equal right hand side and solve for B or for the magnitude. Now, once you have that magnitude, you're supposed to plug that magnitude back into our hypothesized magnetic field, and then you'll have the full vector field. Okay. So now we're going to say B of R times 2 pi R is equal to mu 0 I. Therefore, B of R is equal to mu 0 I over 2 pi R. And by hypothesis, we have B is equal to mu 0 I over 2 pi R in the theta hat direction. And that's how we apply Ampere's law. Again, this is the one case where it's an infinitely long cylinder, and we were just asked for the electric field or the magnetic field outside of it. That's easy peasy. We'll see other examples where we want to know the electric or the magnetic field at different places. Maybe the wire actually is big enough that we can try to detect the magnetic field inside and stuff like that. Anybody have any questions on that Ampere's law example? This is not one of the examples. It's sort of one of the examples in that your book uses it like a derivation to teach you how to actually use Ampere's law, and that's what they're doing on this page, which I'm looking for the page number. I believe that's page 817, or it might have been 816. It's hard to tell because I don't remember if they put the 817 at the top left of the page or if they're putting it at the bottom left of the page in electronic format. I'm pretty sure that's the top, so that would be this is page 816 that I'm looking at. All right, now that I've sort of covered that, give you some idea, I want to show you another example using Ampere's law so you'll have some idea what this is. Now, I am going to go quite long here. In fact, I made this meeting supposed to be 4 hours long, 7 hours. Whew, that's terrible. No, it's supposed to be 4 hours long, so it's supposed to cover your lecture portion and a little bit of the lab time for me to finish this whole chapter. If you guys have to leave, that's completely cool. Don't worry about it, but I want you to stay as long as you can so you can learn as much as you can. I just feel, it's my fault that I couldn't come in today, so I want you guys to have the freedom to leave a little early if you need to. Uh, Technically, you're supposed to be here till what I think it's like 2:10 is what time lab is over. If you leave before that, I'm not going to count you absent or anything. You're good. Okay. Oh, and I didn't tell you, but your test should be finished grading by tomorrow night. And of course, y'all probably get them back since I hand them back to you, meet face-to-face classes. I'll probably give them back to you on Wednesday. And I should have some more labs graded by that time too. All right, again, I'm going to go on to the next example, and this example is example 28.6. Example 28.6 says field inside and outside a wire. A long, straight, cylindrical wire conductor of radius r carries a DC current I of uniform current density in the conductor. Determine the magnetic field due to this current at A, points outside the conductor are greater than big R, and B, points inside the conductor are less than big R, see figure 2811. Assume that little r, the radial distance from the axis, is much less than the length of the wire. And then part C, if big R is equal to 2.0 millimeters, I is equal to 60 amps, and B at R equal 1.0 millimeters, R equals 2.0 millimeters, and R equals 3.0 millimeters, what is the magnetic field? So they're actually wanting you to calculate the magnetic field at those different distances once we've worked out parts A and B. So what we have is basically a diagram that gives us everything. So I'm going to write down the variables they gave us. R is supposed to be the radius of the wire. I is uniform. And remember what that means, just like we learned dq equals lambda dl, or sigma dA, or rho dV. When we say the charge was uniformly distributed, that meant the lambda or the rho or the sigma is a constant. In this case, we pretty much just learned that I is equal to the integral of j dot dA. And when we say the current is uniformly distributed, what they're meaning in this case is the density J is a constant. So if you basically take the total current and divide it by the cross-sectional area of the wire, that number is going to be a constant. So we'd say I over pi big R squared is a constant. That's what we're shooting for here. So let me draw the diagram again. I really like to orient this in the Z direction, so I'll do that as follows. And we're imagining this thing going on for infinity, okay? What we're also saying here is this is a radius r, but we would like to find out at a radius little r, and then again at a radius little r that happens to be bigger than big R. So that's supposed to be the wire we're trying to compute. And what I will do is I will draw this as if this is the Z direction. And this will be the Y direction. And this will be the Z direction. And we're going to imagine that the current is running that way. So I'm trying to show it sort of in three dimensions. I might have made that ellipse a little too thin instead of a little more roundy like that, but and we could have actually made it complete circle in the end. That would have been fine as well, but I just started drawing it that way. Might have been better to draw it the other way. But this is the purple lines are the Amperian loops, and I want to make them consistent with the right hand rule. So I'm going to imagine going around them in the direction shown by these arrows, and hopefully you can make some sense of that. So for part A, B of R for R less than big R, B, B of R for R greater than big R, and C, B of R for R equals 1.0 millimeters. No, it's just 1.0 millimeters, 2.0 millimeters, and 3.0 millimeters for I equals 60 amps. Yep, that's it. And R is equal to 2.0 millimeters. That's what we're assuming big R is. So that's what we're going to do here. Let's start off with part A. Uh, consider smaller, or excuse me, larger in this case because we're doing the R greater than big R first. Didn't know. Yeah, I wrote it backwards on here. Sorry about that. This should have been big R first and little r second. So for R greater than big R and for R less than big R. So consider R, or let's say consider larger Amperian loop. So the larger Amperian loop is this one, and the smaller one is this guy in here. The main thing is you see that I'm going in this counterclockwise direction, and my thumb is therefore pointing in the current direction. So I'm actually integrating in the direction to get a positive current. So that's helpful. Now we'll start off with left-hand side, or actually I'll start off with my hypothesis. My hypothesis is specifically B vector is some B that's a function of R only, and that's our cylindrical coordinate R times theta hat. Okay, now I'm going to say left hand side. Left hand side is the closed integral of B dot dl, which is going to be equal to the integral of B of R theta hat dotted with R d theta theta hat. And of course, we're doing it on that Amperian loop. Okay. And because of that, we get B of R times the integral d theta times theta hat dot theta hat, which is 1. So our final answer is in fact 2 pi r, because the integral of d theta is just 2 pi, and then multiply that by r, that gives us 2 pi r, which is oddly enough exactly the circumference of the path, right? So it's the length of the path times b of r. Now we're going to do the right hand side. The right hand side is equal to mu 0 I enclosed. And since we're doing the big Amperian loop, all of the current is enclosed, so we just get mu 0 I. Now we set left hand side equal to right hand side. That gives us 2 pi r b of r is equal to mu 0 I. So B turns out to be mu 0 I over 2 pi r theta hat, where, and this is for r greater than big R. And this turns out to be just the exact same result that we got on the previous one, which we should have expected because it's literally the same problem. It's a infinitely long wire, and we're asked for a distance r away where r is bigger than the uh, radius of the actual wire, so it should be the same. Any questions on part A? Okay, for part B, we're going to consider the smaller Amperian loop. And we're actually, the Amperian loops really are something that you're supposed to make after you hypothesize the magnetic field. So it's a little backwards the way I'm doing this, but that's because I just finished working that previous example. So you should normally guess by the symmetry of the problem what the shape of the magnetic field is, or more specifically, on what kind of line would you expect the magnetic field to be a constant? And then once you have that, then you make the Amperian loop be, at least in part, that line, but it has to be a closed loop. You can't just do a partial loop. You have to address a line that starts from one point, does some stuff, and returns to that same point. All the parts might not always give you an integral. There might be some parts that give you zero for the integral, and there are going to be some parts that give you a length times a magnetic field. That's the whole point of it. All right. So for this one, we're going to hypothesize that B is still going to be some B that only depends on the radial distance away, and it's going to point in the theta hat direction as we define from cylindrical coordinates again. So now we can say left-hand side is the closed integral of B dot dl is equal to B of R theta hat dotted with R d theta theta hat. And again, because we're on an Amperian loop of constant radius R, we can put the R and the B of R out in front, and we get the integral of d theta theta hat dot theta hat, which is 1. And therefore we get 2 pi R B of R. See, you can just pretty much memorize, and if you show me those terms, then you're certainly going to get full credit, even if you don't necessarily explain why. But if you show me each of those terms that I just wrote out there, as I did in the previous one, then you're showing me that you understand it. And when we get to the solenoid part, there'll be more terms, and that's the important part that shows me you know what you're doing. So just you sort of just memorize that particular part, and then later on, it hopefully will stick in your brain well enough that you can do it, ad nauseum, anytime anybody asks. So now we'll do right hand side. Now the right hand side is a little trickier in this case. Right hand side is mu 0 I enclosed. The I of the wire is not I that's enclosed, because we're actually enclosing a smaller portion of the wire. So how do we figure out what I enclosed is? Well, what we know is J is equal to a constant. And it's equal to a constant because we said specifically the R, or excuse me, a long straight cylindrical wire conductor of radius R carries a DC current I of uniform current density. J is the uniform current density. And you can also say that J is equal to DI over dA. And in this case, since it's a constant, we just know it's I over A. So that's going to be I, the total current, divided by pi R squared. And then J for small loop is equal to I enclosed over pi little r squared, but that has to be equal to I over pi big R squared. So that's what we're doing here. We took the J for the small loop, which is I enclosed over pi r squared, and we're setting that equal to the J that we had for the whole wire, which is I over pi r squared because it's a constant. And now we can get from that that I enclosed is actually equal to pi r squared over pi big R squared times I. And that's what we're going to use. So now we can write this as I times pi r squared. Oh, I need the mu zero in there as well. Let me fix that real quick. I over pi r squared or times pi r squared over pi big R squared times I is the left-hand side. So now we set left-hand side equal to right-hand side, and that gives us 2 pi r b of r is equal to mu 0 r squared over big R squared. And therefore we can say B is equal to mu 0. By the way, one of the R's cancel out over here. This R cancels out with that R over there. We're going to say the B is going to be mu 0 uh, over 2 pi. Oops, why does it keep changing colors on me? Mu 0 over 2 pi big R squared times R to the first power, not R squared, times I in the theta hat direction, and that's for R less than big R. Oops, that was supposed to be red. So that is, and I need to point out what this was used for. In other words, all that stuff down here that I just put that red loop around, that was what went into getting the right hand side. So just so y'all know that that's where it came from. So now I've got the magnetic field for R less than zero. I've got the magnetic field for R greater than zero. And you see in this case that if you let R equal big R, the two formulas match. So the magnetic field is in fact, at least the tangential component of the magnetic field is in fact continuous across the surface. There is an instant where you could have the current flowing only on the outside skin of the wire. If that's the case, then that would create a discontinuity possibly, but we're not dealing with that. So just wanted to teach you that. All right, now finally for part C. Part C, we're supposed to calculate what the magnetic field is for R equal 2 millimeters, R equal 1 millimeter, and R equal 3 millimeter. We'll start off with R equal 2 millimeter. B is equal to, I'll leave the units off this time because we're running out of space. So it's 4 pi times 10 to the negative seventh times the amps are 60 divided by, and I'm using, since the two formulas are the same for R equals R, which is what's going on here, I'm using the formula that we got from part A. So this is going to be 2 pi down here and then 2.0 times 10 to the negative third down here. And that's basically it. And I'll just put a theta hat in it. That way it gives us an actual direction as well. So I'm going 2 pi 10 to, 2 times 10 to the negative seventh times 60 divided by 2 times 10 to the negative third. That gives me 6 times 10 to the negative third. Tesla theta hat. So that's our actual answer for the magnetic field for R equal 2 millimeters. Now, if you look, you'll notice that this formula is also consistent. The 2 pi mu 0 over 2 pi r is exactly the same as the mu 0 I r over 2 pi r squared when r is equal to r. because you end up getting r equal to big R just gives mu 0 I over 2 pi r in the bottom. So it's exactly the same. And because of that, we can see that if we look at the 1 millimeter mark, we're actually choosing r to be decreased by a factor of 1/2. So for, make sure I'm using the right color, for r equal to 1.0 millimeter, b is equal to 1/2 of b of 2.0 millimeters. So it's equal to 3.0 times 10 to the negative third Tesla in the theta hat direction for 2.0 millimeters equals R. So that's for the 2.0 millimeters. And then if you look in the case of part R being 3 millimeters, I think that was next. Yeah, for R equal 3 millimeters, we're basically changing the distance in the bottom because this is now outside. So we're looking at the top formula from part A. We're changing the distance from 2 to 3. That's literally 3/2 as big as R. That means the magnetic field, because it's inversely proportional to R, is going to go down by 2/3 because 3/2 upside down is 2/3. So it should be 2/3 of it. So B is equal to 2/3 B of 2.0 millimeters. And of course, 2/3 of 6 is 4. So this will be 4.0 times 10 to the negative third Tesla for R equal 3.0 millimeters. And that was in the theta hat direction as well. Sorry, I didn't put that in before, but I guess it works good enough there. Anybody have any questions on that one? If don't worry about it, you don't have to catch that quick little trick, so I didn't have to recalculate. You can just recalculate it. It's fine. You just got to know, hey, if I'm doing the 1 millimeter, that's smaller than big R, so I have to use the formula from part B. But if I'm using the 3 millimeter, that's bigger than big R, so I have to use the formula from part B, part A. So just make sure you keep that in mind. I might have said those backwards. Remember, the part A was for R bigger than big R, and part B was for R less than big R. So you got to use the appropriate one. Again, any questions on that? All right. They do a conceptual example. I'm going to talk to you about that one. It says conceptual example 28.7, coaxial cable. A coaxial cable is a single wire surrounded by a cylindrical metallic braid as shown in figure 28.12. The two conductors are separated by an insulator. So this is the wire that comes into your house from either the cable company or the Dish Network or DirecTV or one of those type things, and other things used coaxial cable as well. But if you look at the end of a coaxial cable, what you'll see is a gold copperish wire in the very center, and then you'll see usually some white plastic looking stuff, and then you'll see a little bit of shiny wire, and then you'll see the black housing on the outside. If you look at the end, now that black housing is really just a housing to keep it from deteriorating from the weather and stuff like that. The metallic wire that's actually a braided mesh on the outside, that's one of the actual wires. We're treating that as if current can come from that as well. So you can imagine that's maybe the current going to your cable box, if you will, and then the current leaving your cable box goes back through the solid wire in the middle, and then dead center between it is some kind of dielectric, that white stuff that you see between the copper wire and the silver metal that's braided, if you will. So it says the central wire carries current to the other end of the cable, and the outer braid carries the return current and is usually considered ground. Describe the magnetic field A in the space between the conductors and B outside the cable. So the space between the conductors, let me draw you a picture of this so you'll know what I'm talking about. This is example 28.7. So what we're looking at the end is a copper wire surrounded by some white mesh there, and that white doesn't show up very well, so I'll at least crosshatch it so it maybe shows up a little bit better. And then I'm going to go to a silver mesh of wire around the outside. This is supposed to be braided wire, so I'm trying to show you like the ends of the wire, so hopes that would make some sense to you. And now the housing on the outside is like that. That's what the coaxial cable looks like. This is an insulator. Oops. Now it's normally copper wire, but they could in principle make it to aluminum. They might ultimately do that when copper gets expensive enough. Uh, and then this out here is braided wire. And you might even call it a braided wire mesh. And then housing, and it's usually rubber. Okay, and I don't know why I used the color gray to point to the black stuff. That's not very helpful. I apologize for that. But anyways, so that's what coaxial cable looks like. And what you see is you have basically you can imagine the wire either going into the screen. The current going into the screen in the green wire, or you can picture it coming out. On the picture in your book, it's showing a wire, the current going in. So I'll put a red X in there showing the currents going in. Now, with the current going in, that means the magnetic field line is in fact going to be, I changed this to that, is in fact going to be in the clockwise direction. So between the plates, or between the mesh wire and the solid wire, the magnetic field is going to be pointing in the clockwise direction. And since Ampere's law tells us the closed integral of B dot dl is equal to mu zero I enclosed, we see that the current coming going into the page due to the gray mesh is not contributing at all to this. So we know that the magnetic field B is equal to mu zero I over 2 pi r for uh, between mesh and copper. Okay. So that's the strength of it. Now, once you consider for areas outside of it, so this was part A, and for part B, for outside, you have closed integral B dot dl is equal to mu zero I enclosed, which is going to be mu zero I copper, and then minus I mesh, which gives you zero because the two wire currents are I and I, so they're going to cancel each other out. One of them is consistent with the right hand rule, so it's positive, and the other one's inconsistent with the right hand rule because it's going the opposite way. So that's going to be a negative, and because they're equal in magnitude but opposite in sign, the total current would be zero. Therefore, B equals zero outside of the coax. Any questions on that one? All right, example 28.8 is really a good one that helps you understand some fundamental thing about the magnetic field. So this is example 28.8. Check again to see if anybody's typed any questions they might have. Still no questions? Okay. Example 28.8 says, use Ampere's law to show that any region of space where there are no currents, the magnetic field cannot be both unidirectional and non-uniform. In space where there are no currents, prove that the magnetic field cannot be both unidirectional and non-uniform. So you probably can guess what the not unidirectional means, and hopefully you know what non-uniform means. But this example is going to show you it either way. So uh, let's consider a magnetic field that is unidirectional and non-uniform. Consider B being unidirectional and non-uniform. So what we could imagine is there's a magnetic field that points to the right, and notice the line spacing is getting smaller and smaller. That means it's non-uniform, like that. And the fact that all the lines are pointing horizontally to the right says that they are, in fact, uh, unidirectional. But now, if we consider an Amperian loop, we could make an Amperian loop that goes from A to B to C to D and then back to A. Now we're going to apply Ampere's law. What you can see is integral from A to B is just going to give us, if I call this length right here L, it's going to give us B times L. Okay. Then we're going to have an integral from B to C. And that integral, notice the magnetic field points, or excuse me, the dl points upward and the magnetic field points to the right. That means they're at right angles to each other. And the dot product means that the b dot dl is going to give you 0. So b dot dl equals 0. And now we're going to integrate again. This time we're going to go from C to D. And in that case, we get negative B times L because B is this way, or excuse me, DL is this way and B is this way. So the it's basically going to be times the cosine of 180, and the cosine of 180 is -1. So we get negative B times L. And in this case, we got to realize that B is strong on that first integral because that's where the lines are really close together. And B on that second integral is weak. Okay. So we get B strong minus B weak times L for the left-hand side. But there's no currents here. there are no currents, so right hand side equals mu zero I enclosed is equal to zero, but that means left hand side cannot equal right hand side, which violates Ampere's law. So that's the proof we were shooting for. Because the magnitude at the top would be smaller than the magnitude at the bottom, if they were the same magnitudes, then B times L minus the other B times L would give you zero, which is what it has to be because there's no current here. But in this case, it can't be zero because the two magnitudes of B are different and the L's are the same. So that's what that part is. And then for part, if you want to understand, I don't know why I even considered that part A or part B. That was just a particular drawing, so I shouldn't call that part A. But that's the proof that I did. And what I want to show you is what you can do. So, what can exist? What can exist would be, for instance, a magnetic field. Let's use blue lines. So there's a magnetic field that's not unidirectional. See, they all point to the right, but they point at different angles and that sort of stuff. So that's certainly fine. And in fact, this kind of magnetic field very much does exist. Any questions on that one? All right. It does give you a problem solving algorithm, if you will. So I would recommend you reading that. But let's move on to now discuss the actual magnetic field of a solenoid and a toroid. So we're going to do that via your textbook. It doesn't give this as an example, it just works it out for you. So I'm going to work it out like it is an example. But basically, you can look at the pictures of what the solenoid should really be. But generally speaking, what a solenoid should be is, let's imagine we have a wire coming up like this with a current going into it. And now this wire turns in our direction and starts to come out of the board. So that means it's going to get a little dot like that, meaning the current's coming out of the screen. And then that same current carrying wire is going to move its little booty over here and go into the board or into the screen on this one. And then that's going to come back up and come out of the board, into the board, out of the board. So you can see a solenoid would be like this. So again, out of the board, into the board. So that's what this solenoid looks like. So basically, it's the same thing you learned in grade school when you saw someone take a wire and wrap it helically around a nail. If you then imagine pulling the nail out, what you'd have left is just a solenoid. And actually, it's even a solenoid with the nail in it. In fact, that's one of the things we do is sometimes we put a metal object in the solenoid for a very specific purpose. Like you can use that to make a bell ringing mechanism because you could have it such that when the current goes through the wire, it actually compels the bar that's in the middle of the solenoid to interact with the magnetic field of the solenoid, and that shoves the bar out, and then that bar could run into a bell and go ding ding, and then they could reverse the current, and that would suck the magnet back in, and then reverse the current again and go ding, and then they could do that several times in a second. So you'd hear ding, 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 like that. That's the way it works. But that's basically what a solenoid looks like. And remember, it's basically going down behind, coming out the screen, then it's over one, down behind, over one, down behind, over one, down behind, and it just keeps going like that forever. That is a solenoid. And it's a really great way to make a very strong magnetic field because every one of those wires contributes a magnetic field B equals mu zero I over 2 pi R. And specifically, we're most interested dead center in the solenoid, and pretty much the strength is going to be about the same everywhere. It'll be a little bit weaker off the main central line, but it's still going to be very, very strong everywhere inside of it. And outside of it, the magnetic field is going to be almost zero. So the magnetic field lines, for instance, your book draws, in this case, because you could look at just one. Let's look at zoom in on just one particular part where I have this and then this are right next to each other, and then this and then this are right next to each other. So this is me showing that it curves this way and then comes back up here and then curves this way. The reason why I'm showing it big here is I want you to realize that the magnetic field, according to the right-hand rule, makes a circle so that it points this way here, it points that way there, it points that way there, and it points that way there. And then this one also, the one right next to it, also creates a magnetic field, and that points in the same direction. So I get a magnetic field going that way, that way, that way. But here you see that it's this way. So that right between the wires, the magnetic field is zero. Outside, the magnetic field points to the left. Inside, the magnetic field points to the right. So that's why we get this magnetic field line diagram in your textbook. And really, these go back around and loop again, as your textbook shows. They come back and loop like that because all magnetic field lines form a closed loop, basically. At least for, I mean, there might be a split second right after the magnetic field dies where it won't be a completely closed loop for a split second or two while it's dying, or for a split second or two while it's being built. There might exist some, but they're only split seconds at a time. But the main thing is you see that the magnetic field between the individual coils is zero, and outside it's pointing to the right, and inside it's pointing to, or excuse me, to the left, and then inside it's pointing to the right. So now that we have that, I'm going to use that to calculate Gauss's law, or excuse me, Ampere's law. And I'm going to do it like this. Let's say I choose a path that goes from here to here, and then this one's going to go all the way up to the middle where the magnetic field should be basically the strongest. Now, in this case, all these currents are going into the page, and if I wish this to give me a positive integral, then I want to go in the same direction as the magnetic field due to those wires. So if I use my right hand rule pointing my thumb into the screen, then I'd see that clockwise is the direction of the magnetic field around one of those wires. Because of that, I'm going to choose to integrate in this direction around this closed loop. And we have a top, a left, a right, and a bottom. So now I'm going to go ahead and show you how to compute Gauss's law. So, or excuse me, Ampere's law. The closed integral of B dot dl is equal to mu zero I enclosed, like that. So we're going to say left-hand side. Well, the left-hand side is the closed integral of B dot dl. We've already drawn the loops, and the reason why we drew the loop is we already know, because I drew the magnetic field lines, we can tell what the magnetic field looks like. Our hypothesis specifically is this. B is going to be equal to B of, let's say, let's put a coordinate system like in here somehow. Let's put a coordinate system right here, call that the X direction, call that the Y direction. Then I'm going to say B could be a function of Y, meaning it maybe get a little stronger or weaker up and down, but not a whole lot maybe, but it's B of Y and it's going to point in the I hat direction for inside solenoid. Okay. And we're going to say B of Y is approximately 0 for outside. It's not, I mean, it's not necessarily that it's 0. It's just that it's so monumentally weak compared to inside, because inside we're getting on the order of, dozens of wires, each creating a magnetic field, and they're all creating it in the same direction. So you're getting dozens of times stronger magnetic fields in some sense. So that's our hypothesis. So this left-hand side is going to be an integral of B dot dl for the bottom plus the integral for the right plus the integral for the top plus the integral for the left of B dot dl, like that. So with that in mind, we get the bottom is going to be about 0 dot dl because it's outside, plus the right one, the magnetic field is going to point to, it's going to be either 0 or it's going to point to the right. And the case of it being 0, obviously B dot DL is 0. But in the case of it pointing perpendicular to the DL, it's going to be 0 there as well. So this is going to be an integral of either 0 dot DL, in this case is going to be dy j hat, or it's going to be some magnetic field dotted with dy j hat, but this magnetic field is going to point in the I hat direction. So both of those give me 0, plus the top, which is going to be, in that case, this is the strong part of it. And actually, I should have said this would be a negative there for the right hand side because we're going in the downward direction. But for the top, it's going to be B dot DL is B of Y, or yeah, B of Y I hat dot. In this case, I'm going in the dx I hat direction. And then for the left-hand side, we're going to get the integral of, again, 0 dot positive dy j hat, or B I hat dotted with positive dy j hat. Both of those give me 0. So I end up getting specifically just B of Y times L times the integral of I hat dot I hat, which is equal to 1. All that, by the way, is just times dl, or d, let's call it dx, and then I'll leave the I out, or the L out right now. And that's supposed to be from x equals 0 to L. So the final result is just B of Y times L for the left-hand side. Anybody have any questions on that? That's a little convoluted and a little bit confusing, but you just got to realize on the bottom one, there could be a magnetic field, and it does actually point, in this case, it would point in the same direction, sort of, but it would be a little bit below in some parts, a little bit above in other parts, and maybe exactly parallel in other parts, but it's so darn weak, you're just going to call that one 0. And then, of course, on the left hand side and the right hand side, when you're outside, the magnetic field is going to be close to zero. So below the solenoid, the magnetic field is going to be close to zero. But then inside the solenoid, the magnetic field is going to be very strong, but it's pointing that way, but we're integrating that way. So the dot product gives us zero. So that's why the two sides cancel out. And literally all we're left with is just B of y times L for the top, for the part that's along the axis of the solenoid. Okay, so that's the left-hand side. Now the right-hand side seems a little more complicated, but it's really not that big of a deal. The right-hand side is mu zero times I enclosed. Now, basically the currents enclosed, since we went in that uh, counterclockwise direction, or excuse me, since we went and integrated in that clockwise direction, we know that the I's are all going to be positive, so they're all adding. But instead of trying to count how many are inside of there, what you do is you say, well, what's the number of lines per unit length, or what's the number of wires per unit length? And if we just multiply that number of lines per unit length times the length, that should give us the number of currents. So that's what we do. We're going to say big N is the total number of turns, and big L is the total length of the solenoid, like that. So N over L is the density. Now, if we multiply that by L, that will actually give us the number of wires. Let me explain this with some words. Number of wires per length. So it's a line density, if you will. And then the length, and then we're multiplying all that times I, and then of course we're still multiplying it by mu zero. I should have put that to the left, but I didn't. So the right hand side becomes mu zero, and we usually call the N over L, that's the number of wire, or that's the wire density, and that's usually indicated by a lowercase n, and then times L, and then times I. So now we set left hand side equal to right hand side. And when we do that, we get B of Y times L is equal to mu zero N times L times I. We can see the L's cancel out, and in fact, we see no Y dependence. So we can now say that B is equal to mu zero N times I for inside solenoid. And that's all in the I hat direction as well. So that's how we apply Ampere's law to a solenoid. Anybody have any questions on that? Remember, big N equals total number of turns, and little n equals N over L is the turn density. Okay. No questions on that? All right, now let's look at example 28.9. This is a solenoid. This one's, about the same level of difficulty, but once you see it once, that's pretty much all you really need to do. So, example 28.9. This says a toroid is like a solenoid bent into the shape of a circle as shown in figure 28.17. Use Ampere's law to determine the magnetic field. A, inside the toroid's coil, and B, outside the toroid's coil. So, what we can imagine is I'm going to try to draw it like they did. We're going to imagine a current carrying wire coming down, and then a loop, and then a loop, and then a loop, and a loop, and a loop. And you can see it's really a mess to try to draw. Uh, so I'm going to say a loop. Oops. Might help if I keep it in the pin mode. And it was really stupid because we're trying to draw it and trying to rotate this in a counterclockwise way, and it's not easy to draw that. Let me try it one more time. Now I'm going to say, now this is not going to make a perfect circle, but I think you get the point. Like that. So that's sort of the picture of the solenoid. And if we looked up close, it would look like this. We're going to have a wire where the current is coming out, say on this side, and then a wire where the current is going into the page on this side. And that's just one piece of wire. But then out in front of the page, there's going to be this wire coming over here, and that's going to make another current coming out, and then that wire is going to come back here or going into the board, and then this one's going to come out like that, and it's going to make a big circle where this continues like that. So let me draw this a little bit more precisely. Like that, and hopefully you got some sense of what we're talking about here. The blue goes over to here, the blue goes over to here, the blue goes over to here, so on and so forth. So with that in mind, we see that from the individual right-hand rules, we could see, for instance, that the magnetic field due to this wire points around this direction, and the magnetic field due to this wire going into the board, in this case, points around this direction, which means it's going to point that way, that way, that way, and this way. So the net effect is that the magnetic field line is going to go like this. And in fact, there will be parallel lines to it. Those are magnetic field lines as well. And there's going to be another one, of course, inside, and, an infinity of them more or less. But that's basically what the solenoid is. So now what we're going to see is that the magnetic field B, by hypothesis, why won't it let me write? The hypothesis is B is equal to some B of R. Actually, I should do a lowercase r there. B of R, and I'm going to define it to be in the theta hat direction. And by doing that, I'm saying basically that we could draw a coordinate system. Let's draw this as my whole my whole iPad moved just as I'm trying to do it. So let's say this is the x-axis, this is the y-axis, and because of that, z points into the page like that. And because of that also, we can see that this is the theta hat direction. So so this direction is theta hat. That kind of gives us an idea of what we're talking about. Now we can say left-hand side, the closed integral of b dot dl is going to be equal to b of r theta hat dotted with dl, and dl is going to be basically the radius of the solenoid. So we're going to say this radius right here to the midline is r, and because of that, we're going to integrate along that Amperian loop. So this is B field and the Amperian loop. So we're imagining that's the Amperian loop, and therefore I'm going to put in here is R because we're integrating it along that Amperian loop, and that's going to be R d theta, theta hat, which allows us to pull the B of R times R out in front, and we're going to get d theta, theta hat dot theta hat, which is 1, of course, and therefore we get 2 pi big R B of big R like that for the left-hand side. So again, we got the left-hand side being a magnetic field magnitude times a length. Now, what are the number of currents going in here? Now, the currents are going into the board, and each current carrying wire is contributing to it. And notice that curling of the magnetic field goes the same direction that we're integrating, and the current uh, goes into the page, that creates a magnetic field that same direction. So these currents are all going to be positive, and it's going to be the total current enclosed is in the total number of wires times the current. So the right hand side becomes mu 0 I enclosed is equal to mu 0 times n times I. Now left hand side equals right hand side gives us, oops, gives us the following 2 pi, actually I didn't write that very well, gives us the following 2 pi r b of r is equal to mu 0 n times I. So b is going to be equal to mu 0 n times I over 2 pi r times theta hat, where r is the radius of toroid. Any questions on that one? So notice it looks just like the formula for the regular wire, except it's mu 0 I over 2 pi r. It looks like that formula multiplied by n, but the r means something different here. The r is not the distance away from the center of the wire. The r is literally the radius of the solenoid from the center of the solenoid to about the midline of the coils of the solenoid. So midline is basically what we're drawing there. So anybody have any questions on that one? All right. If you do outside, you'd see that the total current outside is 0. So in doing or in applying, let's say not doing, in applying Ampere's law for R greater than big R, the I enclosed equals 0. So B is equal to 0 for R greater than big R. So that's another result that we should know. But everybody should see that because for each current you've got going into the page, you've got another one coming out of the page. Therefore, they one by one cancel each other out. So the net current is 0 for any Amperian loop we drew outside of R, and therefore the magnetic field outside of this toroid is 0. And that's basically it for the non-Biot-Savart part. They talk about the magnetic field due to a single charge moving. That's just the construction or something you should sort of think about conceptually so you understand. But it's really not much I can ask you any questions on that. 28.8 is magnetic materials, ferromagnetism, paramagnetism, diamagnetism, which we already talked about. In that sense, this section 28.8 is definitely one you're responsible for, but it's all concepts. Okay, so make sure you learn that, learn those concepts as I've already explained them. And then 28.9, they show you applications of electromagnets, and for instance, showing you uses of solenoids to make a bell ring, for instance, or magnetic circuit breakers. Those are all very important, but you see they don't even work any examples on them. The same thing with the section on hysteresis, magnetic fields, magnetic materials, and hysteresis. Those are all concepts, so they're all fair game, but they're again, there's no examples we can work with them. Same thing with the 2811 paramagnetism and diamagnetism. They actually give us some equations in there. I'm not going to require you to understand or use any of those equations, but the concepts are certainly important. So all these sections are part of what I could test you on, but only the concepts for sections 28.8 and going forward. So that's it. We've now finished chapter 28. The rest of the time is just a Q&A session. So if any of y'all want to stick around and ask questions, I'm going to wait till the last person leaves. Everybody else, of course, is free to go. If they don't want to stay, you're still being counted as here. And next time we'll cover chapter 29 this coming Wednesday. And that should be just about it. We've got very little time left. The exams are coming up really soon, but that's it. You guys are free to go or free to stick around and ask me questions for as long as you want. Thanks for coming, everyone. Thanks, Chris. You're welcome.
Hello, Professor.
Yes.
Oh, is it still recording?
Yes. You want me to kill it for a second? You want me to
Yes.
mute it? Okay. Yeah, you're the only one here, so let me not mute it. Let me go ahead and I'm going to stop sharing and I'm going to stop recording.